Okay, good morning, everyone. Sorry for the delay with technical issue. And so bad things come to an end and good ones too. So this is the final seminar of the series for this program. As you all know, tomorrow is the last day of the program. And so I'm very happy to introduce Francesco Giglio from the University of Glasgow. And today he will tell us about some interesting solutions of C-integrable PDEs.
Okay, so thank you very much, Antonio, and thanks to the organizer for giving the opportunity, another opportunity to present my work here. And also thanks to the INI for supporting this amazing program. And I think I can speak from the side of all early career researchers. This has been a great push to and let's say announcement to collaborations and momentum for many of us. So okay, before I start, let me mention that so today's talk is not actually based on a single work, but is a talk based on a collection of things that I have understood together with my collaborators, and it wouldn't be possible without my collaborators to basically achieve any of the work we've got so far. So here just Shin and actually I'm working on a project that is not related to what I'm going to present today. And then there are basically a couple of branches. One focus mostly on the application of statistical thermodynamics of these C-integrable PDEs. And I should say that Antonio actually introduced me to these things, and of course, I mean, it's everything I know is thanks to him and Giulio as well, and Giovanni De Matteis. Okay, so when we work on pneumatic liquid crystals during my PhD in Northumbria. And then there are recent developments, mostly concerning just the solutions and the integrability properties of the resulting class. Okay, so there is Gigi Martina and again Giulio from Lecce and Andrea Zingaro, who is a student of Giulio and Gigi. So let me cliccare sulla pagina e poi dopo.
Slide.
Okay, that's great. Okay, so now that's the outline of my talk. So we'll start with some motivation. So this is driven by classical thermodynamics, and I will somehow show how this classical thermodynamics in the thermodynamic limit leads to formulation of a, let's say, a class of aerodynamic type systems. Then we will discuss C-integrability, starting from actually a need of extending what we know in the thermodynamic limit to finite size systems. And then I will show a prototype of C-integrable PDEs, that is the Burger's equation. And then following that, I'm going to discuss a scalar example of the C-integrable PDEs. And this is a work that basically came out of my master thesis with Giulio Landolfi and Antonio. And I will basically show some generalities, how we derived this integrable model, and focusing then on traveling wave solution and multi-kink solutions. And then following this, I will slightly come back to statistical thermodynamics context, and that will allow me to introduce some example of multi-components integral PDE in the context of real physical systems like pneumatic liquid crystals. Okay, and that will be based on joint work with Giovanni. And so finally, I will just present briefly, basically, how we detect phase transition and classical shock waves when we do the so-called invisible limit. Okay, so some perspectives will follow at the end. So about the motivation. Okay, so basically, typically the first principle of thermodynamics in differential forms reads like this. So a thermodynamic system is specified by a set of conjugated variables. Let's say this x0, x1, xn, okay? And u1, u0, u1, and un. And you can identify a thermodynamic potential or so-called Massieu function, which allows you to basically specify your thermodynamic model. And so then it takes basically this form. So clearly from this differential, so we can notice two things, that these conjugated variables are actually not clearly independent. So you can get UK differentiating this potential, okay? And then because that's an extra differential, there are some closure relations, compatibility conditions, which in thermodynamics take the name of Maxwell's closure relations. And so look, what you have here, so you have basically this, this kind of, differential constraint on these fields U, K, U, J. Okay, so that's quite general. So then basically, if you basically take the index 0, the subscript 0, and you give it a special meaning. So you just distinguish compared to the others. And you call this U0 epsilon, and you assume that this epsilon here is a function of all the other fields plus a irrelevant function of tau 0. And then all the other fields basically are somehow independent in this sense. So, and finally, you call little t this x naught. Sorry?
What is tau 0?
Sorry?
What is tau 0?
Tau 0, yeah, just you basically tau 0 is just the first of this. Sorry. Oh, yeah, you're right. Yeah, sorry. This yeah, tau 0 was supposed to be x0. Yes. Sorry. Yeah, thank you very much. And so basically, if you then assume this thing, and actually here I'm hiding the thermodynamic meaning for now, because this capital T is really the temperature of system, and this epsilon is typically energy associated to a multi-component system. So then you end up with an n-component hydrodynamic type system of this form. Okay. So then what do you have here? So you have basically a set of conservation laws, and the solutions to this system will give you what are called the equations of state. So what we learned from here, that in classical thermodynamics, we can basically obtain an exact in principle equation of state by integrating a set of conservation equation PDEs of hydrodynamic types. And so now the point is that, so the motivation is as follows. So what happens if we want to perturb this first principle, allowing also finite size corrections to describe our physical quantities? And so basically what, so this will be a bit more clear now. And so the answer that I'm anticipating is that we are going to perturb this current here, okay, with some viscosity in the field, okay? And this viscosity here will be associated with the fact that the number of particles of, elements of a given ensemble, statistical ensemble is finite. Okay, and so the strategy, we will look now at perturbation of this laws, or basically a viscous conservation laws, which are C-integrable. Okay, so let me first show a simple example of this book. So, and of course, I'm going to start discussing this question.
What is C-integrable?
Yes.
Okay.
Yes. Okay, so now what do I mean by C-integrability? So Calogero in this thing, it was a proceedings in a conference organized by Zakharov. And so basically in the 90s he introduced this term of C-integrability. So a C-integrable PDE is differently from an S-integrable PDE, so where the S stays for the inverse Cartesian transform basically, is a PDE which can be solved by means of linearization. So there exists a linear problem associated to this PDE, nonlinear PDE, which basically allows you to solve to integrate the equation completely. So now for the burgers, for instance, let's call U is U1. So remember, so that's a scalar case. So n is equal to 1. Okay, so you have two, basically only one field in this case. And then the epsilon is what is inside here in the current. Okay, and so you basically have that. So ut, the derivative with respect to t is given by the derivative with respect to x of this current, where you have a quadratic term here, and you have a viscous perturbation. Okay, this parameter eta is a small parameter. If you send this to 0, you basically end up in one of an example of what we were discussing before, but in the scalar case. So now the point is that this nonlinear conservation law is mapped to the kink equation through this nonlinear transformation, namely the Coulomb transformation. Okay, and so, and interestingly, to basically answer, of course, partially to Calogero question, so with a clear example is that actually these C-integrable PDEs arise very often when treating these statistical thermodynamic systems. Okay, and so let me show you a little bit what happens to the solution. So I took epsilon to be 0.01, and so you can see basically that the initial profile, taking this initial datum, develops a high gradient in the inner part, but the presence of the viscosity inhibits the breaking. And so, interestingly, exactly this initial value problem with this initial datum here was found to be to give exactly the magnetization of a very simple space system, kind of a Curie-Weiss model. When a finite number of spins were considered. And this eta was basically 1/2 times the number of spins in the system. And U basically the magnetization of the associated system. X and T, where the X related to the external field, the ratio between the external field, the magnetic field, and the temperature. And T, the time evolutive variable, was just the inverse of the temperature. So cooling down a system, okay, you increase the time here, and eventually you can end up in a high gradient region. And then this will basically will identify a phase transition associated to the model. So there are most recent developments, actually. Mostly by Antonio, and so there is this first work with Demetris about actually thermodynamics for scalar systems, and then further development, and I basically contributed to these developments into the context of fluid systems and pneumatic liquid systems. So this is basically the structure, okay? So now let's see how we can find additional conservational laws of this form, which are mapped to a linear problem, of course different, just through a Coulomb type transformation. And let's see if we can get far. So, all right, so we can actually, so here there is a list of some references where these systems in the scalar case, in the multi-component case, have been analyzed. So there are lots of examples in space systems, in fluid systems as well, pneumatic crystals, mean-field networks, and random matrix models. I'm putting just a dash there because just a start, because the process is much more complicated. You don't have C-integrability, but still, the idea is that you can get exact equation of state just by looking at the solutions of an hydrodynamic type system. Okay. So, okay. So now, basically, I'm working on scalar C-integrable PDEs and associated physical systems in different perspectives. So today, basically, I'm going to present the original derivation that we did with Antonio and Giulio 2016, and then some ongoing things with the collaborators in Lecce. So if you have any suggestion, please, of course, they are very welcome because we are in the phase of just drafting the final parts. So, okay, so what's the idea? So now we are in a scalar setting, so let's take just one field U, okay? And let's call this the first, the associated determinant variable just X. So we are dealing with just a single scalar conservation law. And let's consider now viscous perturbation of this epsilon. So what I mean, we basically take eta to be a small parameter, okay? And take the current epsilon to be a leading order term plus corrections, which are nevertheless than differential polynomials in U. Okay, so we neglect any higher order correction. Now, the point is that among all possible functions, epsilon 0, epsilon 1, epsilon 2, let us try to find a set of these functions which basically are mapped through a Kolov type transformation to a linear PDE for a potential function phi. Okay, and so the answer is that you can't actually you have the fact that you are including viscosity in the system. You cannot actually add any set of functions, of course, but there is a family of this set of functions, and then it is family of models which allows you to preserve the integrability to the existence of a linear differential problem.
So you're asking linear and with constant coefficients?
No, you are asking linear, and then what happens is that you will get constant coefficient. Yeah, we will come back to this constant coefficient later. That's a very good point. So as you can see, if you kill C4 and C1, you get basically the equation, and then from here you should get again the Burgers. So let's try to understand a little bit some known reductions of this. So this constant that appears here, Cj, are arbitrary constant real parameters. And so if you take the implicit limit, so you basically get a Ivanov type conservation law. Okay, so you're expected to find breaking, so gradient catastrophes and things like that. If instead you take C1, C4 equal to 0, you get the Burgers equation, and then the heat equation for phi for the potential function. If you take instead C2 and C4 equal to 0, you get in a different regime compared to the Burgers one, which is this one, which is mapped to a Klein-Gordon-like equation. Okay, and so you may notice that you have a derivative with respect to a UT derivative, so a derivative of U with respect to T inside the current. So that means that this conservation is not evolutive anymore. Okay, but still this is basically so now let's proceed. And let's try to understand what we have been doing with recently with Giglio and so we have basically started from the full model and redefined the variables in order to get rid of some constants. And so we basically realized that there is this quantity delta, which basically is a discriminant to generic cases and special ones. So if delta is different from 0, that's the generic case, you can perform a change of coordinates with simple transformation, and then you get to something of this form, okay? And that's basically more or less the van der Waals. So what you get from the van der Waals thermodynamics. Instead, if delta is equal to 0, you get to something like this. Okay, and so here basically you get the resulting equation is of cut-like, you can integrate, and the solutions look basically like this. So we will mostly focus on these generic things. So of course, I mean, because we derived that, so this PDE is linearized to follow by this simple transformation. Okay, just to connect to your point, Marco. So yes, indeed, if you actually, so you can rephrase this in terms of zero operators. Okay, these L1 and L2 are two linear operators. And then actually, when you perform this Hopf transformation, you get something a little bit, solution basically for phi are a little bit different. And you have eventually a K0 here, which is a function of t. Still a linear problem, but you have basically, eventually you can take t, as you want, and then of course that's not linear coefficient anymore. Okay, but however, we will basically focus on the case of, constant coefficient, we will consider this K0. So, and now you can recognize that L2 phi equal to 0 is clearly a solution to this. And that's exactly basically our initial linear problem.
So this dot means just product, is not action of L2.
No, it's action. It's this rotor operator is defined on two different functions. Okay. Okay, so basically, I mean, you've got something like
Oh, it's the rotor derivative.
yes,
Yes.
yes, x minus dx prime, and then something like f x t, and then sorry, did I make a mess? Yeah, so f and then g x prime, t prime, then evaluated x prime equal to x and t prime equal to t, and this f and g, f in this case is L2 applied to phi, and g is L1 applied to phi. Okay. So now let me proceed. Okay, so now let me search for traveling wave solutions to these two problems. Okay, because then I want to discuss eventually the presence of multi-kink solutions. Okay, so I introduced the traveling wave coordinate with some constant speed c. So in the case delta equals to 0, I end up with a second order ODE that can be solved, and it can be clearly integrated to get this hyperbolic tangent. So notice that you have basically the amplitude is also appears here. So perhaps this is quite different from what you would get in other single key solution. Okay, I will tell you in a bit. So it's something that is a little bit different from other systems. And so instead, when you consider the case that they go to 0, you get something similar, but it's a little bit more to the solution because you have that the amplitude depends only on K1, but here depends also on the speed. Okay. So let me do a couple of remarks, which will be connected to what we discussed with Apple. What happens? Oh yeah, Glasgow is reminding me to do some update. Yes, fine. Okay, so the amplitude of this kink basically is this form in this case, and is simple form. And then the gradient of the solution actually is a hyperbolic square. Okay, that might remind you something. Okay, in both cases. Okay, but in this case, you can see that there is a square root here, and there is just the square of the amplitude. I mean, we show the amplitude of the kink. It's a little bit. Okay, so this is basically how these solutions look like. I mean, nothing crazy actually that you wouldn't expect. Clearly, the only difference here, I took here a C, which was I think a third. Okay, and then as a consequence, the amplitude of this kink is higher compared to the amplitude of this one. Okay. But then now let's go to a bit more complicated and interesting system. And I will discuss with the construction on how basically we managed to identify these multi-kink solutions. So all right, now we aim to solve this linear problem, basically L2 applied to phi equal to 0. And so the solution to this is a superposition, trivial superposition, okay, of exponential functions, where is theta j here. So these parameters kj delta j, so form a two input of real parameters. These theta j here are given by kjx, and then a frequency, which is the inverse of kj, okay? Plus a delta j, which in this system is just a, an unrelated parameter. Okay, we will go back, when we discuss a bit of statistical thermodynamics to see whether in some cases this delta j is constrained to be a function of kj or not. So now you apply the Kolov transformation to this, and you write the solution as a kind of projection of the different states on this weight function w. So these weight function are defined as the ratio between the exponential of theta j and the overall function phi. So why am I calling that a weight function? Because they actually fulfill this kind of normalization thing and remind some kind of probability. Okay, but here we are not talking about any statistics. So now, what's the point of writing the solution in this form? So the solution is written in this form because when we take eta, the parameter eta, to be quite small, okay, so what we have is that we can identify some regions of the x and t plane, okay, where, for instance, the region Rj is the region in which theta j is larger than all the other n-1 j's, thetas, okay? And then when eta is very small, the solution is approximated by kj in each of these Fj regions. So these Rj regions, okay, are disjoint. So the collection of this will give you an open set actually, and will allow you to approximate the union. This capital R will allow you to approximate the solution in. This is not completed yet because I'm not saying what happens at the boundaries of these domains. Okay, so yeah, maybe I should say why this is the case. So that's the case because so remember that you have basically something like this. Sorry,
it's the ratio between that and the sum of all the components.
Yeah, so yeah, exactly. So you have basically something like this, okay? So this phi n, and so you divide by in the region where this is bigger, you divide by this exponential, okay? And so then you get 1 plus something which goes to 0 in the limit of eta small. Okay, why? Because then you get e theta, let's say L minus j, and that's a negative quantity divided by a very small number. Okay, so then yes, please.
When you define your capital X and capital T, do you rescale them by eta or not?
No. Yes, I forgot to mention something. In the multi-kink, in the previous case, the traveling wave solution, I said eta to be 1. Sorry.
Now it's there.
No, now it's there. Sorry?
Okay.
No, now it's there. I mean, here for the determination of these regions, eta is not important actually. Okay. So you don't need that. Okay. Yeah. And so now let me do just a remark. Okay, maybe I should just finish here. So you basically get kj 1 plus, and then you have something like a summation for all L different from j of e theta L minus theta j over eta. Okay, and this basically is negative, and it's very big in margin, so it's good in zero. Okay. Okay.
Theta is important.
Sorry.
Theta is important because you're taking the dominant.
What do you mean?
Yeah.
Yeah. I mean, this is in the Rj. Okay. So that's just in J. And then you consider the solution approximated in the various domains. These are disjoint. Okay, so now what about the line? So the thing is that look, you have the boundaries of so the boundary for this relation here. So So theta j greater than theta I for all I different from j. So basically set up some lines actually in the x and t plane. Okay, and so you have basically that the boundaries between different regions are line segments which are defined like this, some kind of resonance formation. And these line segments represent the trajectories of classical dissipative shock waves with velocity, which is given by the parameters, basically the velocity of the shock between a state I and j is given by minus the inverse of this product. Okay, and that's exactly the slope of the boundaries. I will show you some examples. And so it's interesting also that because eta is very small but finite, you can actually get an estimate of the solution along the boundaries. And that's basically you can have a kind of average rule. Okay, something you cannot construct in the limit eta 0 because the solution is discontinuous there. So, okay, great. So now I want to basically discuss a little bit some conservation laws. I won't succeed in finding all conservation laws as one will do, for instance, for the KDB case, but I will just find a couple of them for now, okay, which are still relevant for the description that I'm going to show you. So let me define the mass density as the gradient of the solution and the momentum density as the gradient calculated with respect to t. And so then if you basically calculate the total mass and the total momentum, these are conserved quantities, okay? So these k plus and k minus are the asymptotic states when x goes to plus and minus infinity. And these are actually constant because these slopes are basically, these slopes are non-zeros. So that's why you have a clear determination of this. And then it is nice to basically notice that you can basically take along these trajectories of these shocks, you have a relation between the momentum, the mass, and the velocity. Okay? And so, and in particular, if you consider the overall, the total mass, total momentum, you can introduce a kind of effective total velocity, which is given by the outer weight numbers, k plus and k minus, and you have this very simple relation. And so, basically, what happens, and I will show you the dynamics, is that you can establish a kind of duality between shocks, interactions, particle interactions, scattering processes. Okay, and so for the conservation of mass, you have simply, if I define the mass, as you can see, of a shock between a state I and j as ki minus kj, you have clearly that if you put an intermediate state, you basically get that's the same as before. And then that's understood as basically the mass of the particles before and after a scattering and a collision process is the same. And then the same for momentum. Okay, here you can verify this very simple relation. So that's actually, this summation is a bit more general. This is just an example of a shock fission. So a shock which is dividing into different shocks. Okay, so now this is basically what you get. So this is a case of n equal, yes, please.
You will be back to the previous slide. Probably a stupid question, but you write that the momentum is conserved, but then you say the scattering is inelastic. So
yeah, I mean, it's inelastic in the sense that the internal state of the particle change, but the energy is still somehow conserved.
But the momentum as well.
Yeah, but it's the kinetic energy. Okay. Yeah. So, but you have yes, but okay, you have basically different particles before and after the scattering process. If you integrate, basically, you basically would get the mass and momentum is conserved. So inelastic in the sense that the internal states of the particle change. which does not mean that necessarily this implies a loss of energy. Yeah, so, yeah, but that's a quite really cool thing. Sorry. Okay, now let's look at this example. So on the right, we have this simple geometric construction. Okay, that basically is the collection of 4 different regions. Here, I wanted to show an example of 5 of such terms in the linear solution. And as you can see, there are 1, 2, 3, only 4 regions. So because you have that the region is obtained by the intersection of all this half half planes, okay, not necessarily all the terms, all the wave numbers that you put into your solution will appear as an approximated state. So in this case, there is one of the wave numbers which is exactly not visible from the process. So on the right, basically, so you can see that very nicely. You can get or you can calculate the intersection, so where the shock occurs, and you have this quantities here with a kind of Vandermonde determinant at the denominator and some kind of symmetric products here. And these are entirely given, of course, in terms of the parameters of the solution. And on the left, you have the Excel solution, okay, with an eta which has been taken to be not super small actually, because I wanted to show there's half. Okay, I wanted to show that there is a finite transition region between different states when you consider eta to be finite. And so clearly, as small as eta and closer, this will look to this the pattern on the right. So now, okay, maybe let's look at the dynamics. So I start from yeah. So that's you can see. Okay, yeah. So from -15, something from here, you can see that there are 2 states. One is state, let's say, to be kind of 1, K1, yeah, K2 equal to 1, I think, yes. And on the right, you should have K5, which is equal to 4. Can you see? Asymptotically, you have 4 and you have 1 here. And so then you have also this one to the left, because if we consider a larger portion of the X-plane, we will basically end up measuring actually this other state here, which is K1 equal to -1. Okay, so now if we basically let this thing evolve. So this is basically what we get. So look, initially you have you have 2 kinks. Okay, finally you have only 1 single kink. In the middle there is a transient kink which appears. Oh, sorry, which appears at some point here, but then disappears. And then basically this is nevertheless then the state which is highlighted with K4. Okay, so it's a kind of, you can see this as a kind of scattering process where the initial and the final particle do change with some transient state in the middle. Okay, let's look at some more complicated case. So if you look at some more complicated case, this is a case n equal to 8. And I basically made this solution, starting from n equal to 2 and then progressing this using the fact that we know how to calculate all these points of interaction. And in particular, basically what I made here, I tried to look for higher order resonances. And then in this case, you can see that you've got 2 shocks, which end up in other 2 shocks. And what I'm trying to do here is to mimic a system in which at the end, I can have a kind of the same particles before and after the shock, the scattering process. Okay, because I want to see what happens compared to what can happen for some interaction between 2 solutes. And so that's basically what you get. You have a very complicated things, but eventually at the end, you have 2 kink initially and 2 kink after. And the amplitude of the kink, you might notice that this amplitude actually finish to the left, travels to the left. Okay, so that this kink travels to the left and then emerge towards the left. and these actually emerge to the right. So now let me look at the momentum. So I mean, I'm sorry, it's not visible. Sorry, the mass. Okay, so that's the gradient with respect to x. So that's what you have. And basically you have an interesting kind of, can think of a scattering process where there is a complicated interaction, mass is conserved and momentum is conserved. So that's instead the momentum. Okay. Yes, please.
So here, I would expect being linear, there is no phase shift. Or is there?
That's a good question. Yes, actually depends. You cannot even, so typically you would expect no phase shift, but it depends on how you define phase shift. Because the phase shift typically requires that you have the same particles before and after, same solitons, same height, same parameters before and after. So here, in general, it is not. However, in this case, I basically I chosen the parameters such a way I could measure that. And the answer is that there is a Galilean phase shift in the end. Okay, but it's not, it's something that, before actually, we didn't find an exact formula to this. It's something that needs to be discussed. So this is the momentum, and as you can see, correctly, the momentum from the right is negative because the velocity is negative, and then basically there is this nice pattern. So, this is, you can do the same also in the case of, for the case of delta equals to 0. Okay, the singular, so the special case. I don't want to discuss this too much in detail, but just I want to point the fact that in this case, the velocity, the frequency is the same for all k, because you remember that the structure of the solution was much more simple. Okay, and so what does it mean? It means that you can have also particles at rest. And that's basically an example. So if you wish. So let me show you a little bit what happens. To the left you have the behavior of the of the solution, and then to the right you have the behavior in terms of the mass density. Okay, so you have in the end a fusion of 4 different shocks. Two different shocks. Okay, so now I will basically give a little bit. Will not go too much in detail for time constraints, but I just want to give the kind of taste of the C-integrable models in the context of statistical physics of a well-defined statistical object, statistical model. So that's basically on the mathematical quizzes with Giovanni and Antonio. So these 2 papers actually regard 2 different eigenvalue type system. One is a 2-component system, and one is a 4-component system. Okay. In both cases, we managed to find exact solution and the associated phase diagrams. That is the shock trajectories of the system. So the main motivation is that, so the main point is that the partition function associated to this the system obeys, and here, so beta is 1 over the temperature, H is the Hamiltonian, N is the number of particles, in this case, it's liquid crystal molecules. And so the idea is that you can write the partition function as a combination of exponentials. So interestingly, so the argument is also linear, but now not only in x and t, is linear also in x and y. Okay, and so then you have that this capital M somehow measure the field variable, so the analogous of the magnetization, but in this context is a kind of it's a kind of ordering parameter of the system. So it's an average quantity, and the partition function fulfills this 2 components, so this 2 plus 1 dimensional heat equation. Okay, so when you have you have to just perform a change of coordinates to in a standard form, and then the initial condition
which you can see that this lambda I1L, lambda 12, it's a kind of analogous of this K parameters of before, which are fixed by the initial condition, is such that the system under study is basically the physical system. So it is consistent with the physical system and the thermodynamic. And so you basically define free energy as the 1 over n the log of the partition function, and you get that the order parameters, let me call them n1 and n2, are the expectation values of this variable capital N, okay, and are obtained just by taking the Kolov transformation of the partition function. Okay, so again, partition function, which is basically my potential function, is now a physical object and obeys a linear PDE. Okay, and associated to that, there is a nonlinear problem. So then, okay, you can get exact solutions. I'm not providing details of this, but clearly, if you want to look at what is the corresponding hydrodynamic type system, you basically get that you have some 1 over n, which is typically very small, which gives some viscosity into these conservation laws. Okay, and so that's basically what you get for this particular system at different times, which means lowering the temperature. Okay, so lowering the temperature, these two components, N1 and N2, basically develop a high gradient region, which becomes much thinner when you decrease the temperature. Okay, and so. Okay, I'm going to skip the 4 component case, but you can essentially do the same here. And so what is important is that when you have so in this statistical thermodynamic systems, you have this physical parameter n. Okay, and what makes sense is to consider the so-called thermodynamic limit. So you send n to be infinite, and then that means that the viscosity in our equation is not considered anymore. Okay, and so basically, if you do an expansion of the free energy, remember was the log of this potential function, you end up with again a system like the ones that I showed you at the beginning. For 2 fields, in that case, let's say N1 and N2, but that's a general thing with the n fields, and you can basically get an explicit expression of the free energy if you manage to get this W function, which is associated to the initial condition. So it's a quite nasty problem. And then the solutions basically can be written in autograph form. Okay, that's if you manage to actually get this W explicitly, and the critical points of the statistical model, which means the points in which there is a gradient catastrophe of the solution, can be obtained by means of singularity theory. Okay, so all right. So briefly, the gradient catastrophe for a scalar case, if you define this map from basically the fields to Rn, takes basically this form, and in the scalar case, the condition to have a breaking point is quite simple. In the 2 component case, these are given in terms of witness theory, so for singularities of maps from the plane to the plane, and a quite difficult task is to go beyond for higher order, so higher component systems. Okay, so yeah, okay, let me just show you a little bit what happens at these 2 components, M1 and M2. So when you basically in the thermodynamic limit, when you decrease the temperature, so initially a very high temperature, you have that these solutions, let's say M1 and M2, are just one to one. Okay, so you can for each time t, so there are a single value. But then when you increase time, you eventually get that this surface basically starts to develop, so starts to fall on itself. And the points where this happen will identify exactly the point where the gradient catastrophe occurs. Okay, let me just show you what's the dynamics. So I've been showing to many of you actually this thing, but I wanted to present this again in light of what we have seen today in the scalar case. So this is the dynamics of the cast points, which are the breaking points for associated to a two-component system. So basically, initially, when the temperature is very high, so you have these 3 points where the gradient catastrophe occurs, which starts from very high values of the fields x and y. Then they make these corners and 2 additional breaking points, of course, and then they annihilate in the middle here, here, and here. And this annihilation, it's probably a conservation of mass and momentum, if you see these as particles. Okay, so we didn't analyze that in detail when we work on this. And so, and now, basically, when you look at the various points where gradient catastrophe occurs, like in this case, after that, in the thermodynamic limit, you get multi-valueness, and you can get basically, you have the formation of classical dissipative shock waves, like in this case. For that's a case in which you take x equal to y, and so you don't work in full x and y plane, you work along the directions. And then you basically observe the formation of shocks and the collision of shocks as well. Okay. So and then interestingly, if you at each time temperature, you take note of the position location of the shock and you do that continuously, you will end up with shock trajectories associated to the specific model understudied, which nevertheless give no less than the phase diagram of the substance. Okay. In this case, you have 3 phases of the system, basically that are called uniaxial uniaxial minus uniaxial plus and biaxial. So let me just conclude saying that so you can get similar things for higher order models, reducing to a smaller components one if there is enough symmetry in the system, and in most of the cases you can get singularities in explicit form, like in this case we have basically this phase diagram where this red line is given by the cusps of the model, and you can see that where the cusp occur, this basically and is visible. That's a second order phase transition, in the sense that all the parameters do not jump, but their derivatives do. So perspective. So I mean, I try to show a class of C-integrable models in the scalar and in the multi-component case. These arise typically from statistical thermodynamics, but you can detach them from the statistical meaning. They arise as viscous conservation laws, and you have some mapping to linear problem. So the point is that if you focus on the statistical thermodynamics of a classical system, basically you are interested mostly in the shock formation, so when a phase transition occurs. Now, the point is at the very end, following the analysis we have been doing on multi-kink solution, is on thinking on how to make a classical system, a simple system, complex. Okay, so how can we do that? So, for instance, we can allow this wave numbers case, let's say, to obey to a probability distribution function, even probability distribution function, And that would mean that if you think of this as a statistical system, that would mean that you don't have actually, so your system might behave differently. So you don't have precise configurations of your systems because the wave numbers, as we showed before, were corresponding to macroscopic configuration of the system. Okay, so I don't want to just run much more over time. So thanks a lot.
There's the pictures of these, planes, intersections, and so it reminds very much of the work of Yuji Kodama.
The recent one,
Well, also recent.
okay, yeah, the line about line solid and so.
Yeah, line solid, right, because the combinatorics is essentially almost the same, except that the phase function. But so the question is, by looking at these type of tropical limits, in the case of KP, or in the case here, so is it possible to see some qualitative history?
There is actually a discussion with Antonio about this in order to see these basically cases as reductions because if in KP you have X and Y. So here we have been discussing just one special variables. So it might be that I mean actually also Yuji was mentioning to me that if you get something like that, it's because there is KP on top. And then, so in this case, you don't have actually workers. You have something very similar though. I mean, the mechanism of formation of this solution is very similar to workers, although they are different. But yes, I agree that there must be a connection. But even this very simple, I mean, this simple thing that I showed you about the multi-kink, the emergence of this multi-kink, something that we are still finishing up, so but it does have to be investigated. Thanks a lot.
I think here you need like the third variable, the evolution in time. This is the projection.
Right, as the plots in the XY plane are.
It's exactly the same mechanism because in the
dominant.
you solve a set of linear equations, the Sato equations in the Wronskian solution, and here is a different linear mechanism is not the same, but the mechanism is the same.
There is another example of famously generalizable C-integrable PDEs, which is reveal. Do you think you can apply this to reveal?
Sorry, example in which
Equation.
So this is a Euclid equation, is a PDEs that you can also express.
Okay, as a linear. Okay, I don't know, to be honest. It's something that so is the mapping the linear mapping different from the player?
Yeah.
Okay. So I think so, because I think what really matters here is that you have an underlying superposition principle. So you have I mean, at the level of the linear problem. So as long as you have a linear problem underlying the structure, I think it means that linear problem, so you can add as many terms as you wish. Okay. And then see basically what happens in terms of the linear one. But I think it might be possible.
So a little bit along this line of thought, but what if you take the problem from the other end? So you take a linear E and then you choose the non-linear transformation in another way, not logic. Is it possible to characterize such transformations so that you get some reasonable PDE non-linear?
So reasonable, what do you mean reasonable?
The question. So you want something maybe hyperbolic or
Okay.
but changing the log to
Something else, yeah, that you can eventually, but the point is that, so, okay, I mean, here, I wanted to stress the motivation behind it, because we don't choose a color transformation, okay?
Right.
So it's something that arises because of the form of the averages of these order parameters in all these models, okay? So it's not something that we choose. It's something that Antonio observed first, and we said, okay, can we mathematically extend the family to and then identify the underlying physical system afterwards. So that was the idea, yeah, but yeah.
I think the special thing about the Coulomb transformation is that the function, the transformed function is the free energy of the physical model. So this is, if you take another one, of course you can take a linear transformation, but what is the physical interpretation of this? So it's like the partition function satisfies the linear equation.
Right.
And then when you differentiate the log of the partition function, you get the order, what are physically defined as the order parameters. So they are the averages of the quantities. It's something special about Coulomb in
Yeah, I mean, even this construction, I mean, even, discussing the problem without thinking about this n-term function as a partition function, yeah, if you consider the cohort, you can introduce these weight functions. Okay, but again, you can do that, and there is a reason why you can do that. So it's, yeah, I'm not sure that there would be such simple description for our linear transformations, but.
More questions? If not, let's Francesco again. Enjoy the rest of this very wet day.